go to current slide. I'll even turn on the projector, I guess, today. I'm feeling maintenance. And wrong one. I haven't taught this class in a few years, decades. Okay. There are a few announcements. Some of these are fairly important, I think. Hopefully will be to some of you. First and foremost, I guess, in some order, I guess this one is pretty important. Tomorrow is the day that we are required to turn in incomplete grades, update the incomplete grades from last term. So if any of you have an incomplete grade, or if you know of someone who has an incomplete grade, got to get it covered today because tomorrow we turn them in, okay? And I don't think there's any budging on that deadline. So please get something in today, okay? Number two, speaking of tomorrow, normally I'm on the Birmingham campus 8 to 12. We'll be on the Birmingham campus tomorrow. I just don't know what time. I have a doctor's appointment at 9:15. I'm figuring it'll go until about 10:15. Hopefully not much later than that. And I don't know now whether I'll go to Birmingham campus before that and then drive back. I'd have to leave by 8:45 to get back, and that's going to be pushing it. But after the appointment, I will be going back to the Birmingham campus. So I figure I'll be there 10:45, 11, somewhere in that time frame, okay, depending on how the appointment goes. I don't think it should be long, but I don't know how backed up and how slow they are or anything else. It's a dermatology appointment. I haven't had one in years, many years. So anyway, so I don't know, but I think I'll be there 10:45, 11 or something like that. Now, I may be there 8 to 8:45. I don't know that yet. I haven't talked with my boss, so I hope to get in touch with him today. Okay, that's this Friday. Next Friday, I won't be on either campus at all because I've got a meeting I'm required to go to down in Mobile, Alabama, and I have to leave home probably around 7 in the morning, and I think it's a 4 to 5 hour drive, and so I've got a 3-hour meeting and then another 4 to 5 hour drive back. So it seems like an enormous lot of time for a very short meeting, but I'm required to be there. So next Friday I won't be on either campus at all. The following Friday I have an eye appointment, and that's right across the street here in UAB West Hospital. So that's 8:15. So I'll probably come into this campus first, head over there, have my appointment, and then I'll find out whether I need to go back to Birmingham or stay here. I don't know what's on tap. And very close to that is spring break. So not going to be too many extra Fridays in there. Now, that takes care of my weird Fridays now for a while. One other thing coming up next week, and I don't think any of you are in any trouble at all, though I can't say that for sure. I know no one's in any trouble, but let me just explain what's happening. Tuesday night about midnight is exactly midterm, okay? Because Tuesday is the last day for first mini-term classes, Wednesday's the first day for second mini-term classes. So somewhere in there is midterm. Sometime after midterm, usually very soon after, they ask us to report midterm progress report, which means anyone with a D or an F at midterm, we have to, turn those names in. Now, that really doesn't mean a lot, but if we have to turn your name in, then you may be getting messages, phone calls, people trying to contact you to find out what they can do to help you get your grades up at midterm, after second half of the term. And so it may be a little bit of a hassle for you, but now, here's the deal, folks. I've gotten one UNO research paper in, and I've gotten in, it looks like probably a little over half of the first test. But if I don't have a score for you when they require this, that's a F at midterm. Not that I think you're going to make an F, but that's what I'd have to turn in. I don't think anyone who's turned in the first test is in any danger whatsoever, so you're okay. I don't foresee many Ds, but I see a few F's out there if I don't get something by the time they request that, which is usually sometime next week. So get me your research paper and or your first test, if you haven't turned in anything, sometime soon, as in today, tomorrow, or early next week. Make sense? All right.
The research paper is the same as last semester, right?
Yeah. Well, yeah, all the instructions are out there, but it's not the same paper. Okay. What's that? No, that's why I keep them, remember? Oh, yeah, I remember that. Okay. All right. That's not why I keep them. They require me to keep them, but it's an added advantage. Okay. So, any questions before we get started on today's stuff? Sorry we're so late getting started. Still in Chapter 4, but just about finished with Chapter 4, Trigonometry. 4.8 is Applications and Models. No, not that kind. Okay. The objectives of this section: solve some real-life problems involving right triangles. Solve some real-life problems involving directional bearings, whatever those are. And solve some real-life problems involving harmonic motion. And of course, you're modeling real-life stuff with problems, with trigonometry functions, which we've done at the end of just about every section, but now we're going to do a few more. So let's start with applications involving right triangles. In this section, the three angles of a right triangle are denoted by the capital letters A, B, and C. Quite often we've been using Greek letters, but now it's capital letters A, B, and C. Where C is always, if this is a right triangle, C is always the right angle. So we know it, okay? You don't really even have to label it C, but we know that that's the right angle because this is the right triangle. The lengths of the sides opposite these angles are the lowercase letters. So if you have an angle over here, A, the side over there is little a. The angle up here is B, then the side down here is little b. Now, of course, wherever the right angle is, the side opposite that, which has a special name. What's that? Ah, there it is. Hypotenuse. Okay? That is always side C. Make sense? Okay. Where was example 1? Okay? They skipped it. So let's back up. Well, I don't know if I'll have one with any more room to write. No. So let's just do it on this one. We'll do example 1 first, then we'll come back and do example 2. All right. All right. Example 1. Now, this is one of those that you can see larsonprecalculus.com for an interactive version of this type of an example. So either this exact example or something like it will be given. Solve the right triangle shown at the right for all the unknown sides and angles. Okay, so I'll even draw it on the right. Okay, there is a close to vertical line. Here is a somewhat horizontal line. And there is a line that connects those two. Okay. Now, what they tell us, this is angle A, this is angle B, and of course this one is always, the right angle is angle C. Which makes this side over here A, this side down here little b, and the side, the hypotenuse, little c. Okay. Now, what they tell us about the problem is that this angle A is 34.2 degrees. 34.2 degrees. Okay, what they tell us about side B is that that is 19.4 units. We don't say what units, but 19.4 is the length of side B. That's all they tell us. But we do know one other piece of information. What's that? Right angle. C is a right angle. We know that angle too. So of the remaining 3 pieces of information, which we're supposed to find all 3 of those pieces, little a, little c, and capital B, which of those is going to be easiest to find? Second? Capital B, why? A little up. Okay, that's exactly right. But there's a couple of reasons, okay? One reason, the sum of the three angles of any triangle, whether it's right triangle or not, is 180 degrees. And since that's 90, then the sum of this one and that have to be 90 as well. Or the other way, if you remember this, these two angles of a right triangle, the two acute angles, are complementary because they have to be added to 90. So what would be B then? And my picture's not to scale, by the way. What would be B? Anyone do the math? Second? 55.8 degrees. So there's your capital B, 55.8 degrees. Those add to 90. Those are complementary angles. Perfect. All right. Now, of the other two, there's several ways you can approach. What would you suggest? Which one do you want to go for first? A or C? I don't really care too much. A. A? Okay, I like A. All right. I like A's better than C's. No. Okay. So, to find A. Now, there's nothing that we can do right now to get that directly except for a, and what's the name of this course in this chapter? Trig function. Okay? Now, what trig function relates, and here is my little prejudice here. I want to use this, not that. Why? You may have made a mistake giving me that answer, and I'll trust not that. Okay? I know that answer is right because they gave it to me. So I want to use this angle to find that side. How can I do that? What's the relationship between this angle, that side, and we need something else? Maybe some other side we know? Tangent, exactly. Okay? And how does that go? The tangent of 34.2 degrees is what? What is tangent? Opposite, which is A over adjacent, which is 19.4. There we have it, right there. So what we can do is multiply both sides of the equation by 19.4. This will wipe that out, and that leaves us little a is equal to, you pull out your handy-dandy calculators and see what 19.4 times tangent of 34.2. Be sure that you're in degree mode. I don't want any weird answers that are in radio mode. This one's in degrees.
It's 13.2.
13.3, is that what you said? 2. 13.2. 13.2. Now is a good time to take a short break here, and obviously mine's not to scale, and see if this even makes sense. Okay? And here's what I use to see if it makes sense. This, obviously, is the smallest angle, right? So this is true in trigonometry, that the side opposite the smallest angle has got to be the shortest side. And sure enough, that is shorter than this. That doesn't tell you it's right, but at least it tells you you're in the right ballpark. If this had come up 31.2, you know it's wrong, okay? So at least you got the right frame here. Now, we got two of the three unknowns. The third one, side C. There are multiple ways to get it. How would you suggest? Any recommendations? I'll just leave that in blank. Okay. How would you get C?
That's how I do, so it would have to be cosine or sine. Right?
Okay. Yeah, those would work. Which you want to use? I have a preference, you might guess.
The one given?
The one given, of course. And what would that be then?
1984.
Yeah, the 19.4 is given. Which is that? What'd you say? Someone said something.
B is given.
Second?
55.8.
Okay, that, yeah. Again, that's probably correct. I really do trust you, but I want to use the ones given. So,
Yeah,
so angle A. And then what would be the relationship? Which trig function you go use? Cosine. So cosine of A is equal to, what's cosine? Adjacent over hypotenuse. So this will be, adjacent side down there is B, which will be 19.4 divided by C, which is what we're looking for. Of course, A was 34.2 degrees again. So again, to get what we're looking for, this time we multiply both sides by C. Okay, that wipes out the C here, but here we're needing to divide by cosine 34.2. All right, and this will wipe this out on this side, leaving us a naked C, which is what we want. C is equal to 19.4 divided by cosine of 34.2. What does that give you? 23.5? Does that even make sense? What you know about the hypotenuse?
It has to be the biggest angle.
It's got to be the longest side because it's opposite the largest angle. You're absolutely right. And it is larger than those two. That doesn't guarantee it's right, but at least it makes you feel warm and fuzzy, right? Now, what's another way you could sort of do a little check to see if they might be right?
The Pythagorean theorem?
Second?
Pythagorean theorem?
Yes, exactly. So just check and see. 19.4 squared plus 13.2 squared. See what that is. And then square 23.4 and see if it's the same thing. Good check. I always like to check for it to make sure it's right. I hate making mistakes. Y'all make a lot of them. Okay? And guess what? I don't want y'all making mistakes either. Because good, correct papers are easier to grade. And I want them easy. Okay? What you get? Are they the same?
Yeah.
They are the same. That makes me feel very good. Now let's see how the book did. They got the side B, angle B was 55.8, good for them. Y'all were reading out of the book, weren't you? Okay, and then they got A was 19.4. What? They got that misprinted. Oh, no, I'm sorry. I didn't read the whole thing. So, where is the little A? 13.2, good. They got that right. And then they got C equal 23.5. Well, we got 4, they got 5. I bet you it's a round-off error involved somewhere there. Don't you think?
Yeah, they're wrong.
Oh, you know how they got it wrong? No, they didn't. They shouldn't have gotten it wrong. They used the same thing we did. So, I don't know. Someone just did a round-off error. They did or we did, but it's not bad. If you get that close, it counts. Government work, you know. All right. Got it? Not Honda work. Okay. Okay. Any questions before I erase it? Got it? All right. Here's example 2 then. A safety regulation states that the maximum angle of elevation for a rescue ladder is 72 degrees. Frankly, I don't even want to go on at 72 degrees. That's pretty steep, okay? A fire department's longest ladder is 110 feet. What is the maximum safe rescue height that they can go up a building? Okay? I think pictures are worth thousands of words, so let's see what we can draw. Let's pretend this is the building here, okay? And pretend this is the ground down here. Now they, in their picture, I think, no, they don't have a picture here, do they? You know, their example 2 is not this example 2. Yeah, well, let's do this and then we'll do the example 2 from the book. Okay? The picture that used to be in the book here had it from the top of a truck. Let's just have it from the ground. Okay? Now, I tried to guess at that to be 72 degrees. That's the maximum we can. And the longest ladder is 110 feet. Now, we're going to make a little assumption here, and it's usually pretty good, that the building is vertical. Okay, that's usually pretty good. And that the ground is pretty close to being horizontal. If that's the case, we're going to assume that's a right angle. Most of the time, that's going to be pretty good because they usually do it. Generally, land does slope away from a building, so you don't have water going back into the building. So it might be a little off, but that's going to be the best we could do here. Okay? So what are we looking for? How far up the building this goes. You want to call that H, maximum safe rescue height. Any way we can do that? Here we don't have to figure everything else. Let's just figure what they're asking for. Okay, we don't have to get the other angle. We don't have to get how far from the building. I don't think they asked that. No, it's not there. What is maximum safe rescue height? They could have asked the question, how far from the building should they put the ladder? That would have been a good question too. They didn't ask that, so we're not going to do it.
72 degrees sine.
Say again?
72 sine of 72
degrees. Got it. Because that's the opposite side, we're going to go with the sine of 72 degrees is going to be what?
It's going to be 110 over H.
Oh.
H
Huh? What is sine? Opposite over hypotenuse. And which is the opposite? Which is the hypotenuse? H is the opposite. Hypotenuse is opposite the right angle, so that is 110 feet. Okay? And to solve this, multiply both sides by 110 feet. And there you have it. H is equal to 110 times sine of 72 degrees. Anyone get an answer?
It's 104.6.
One over what?
104.6.
Okay. I heard 104.6. Okay. Now, the most you have significant digits here is 2, and you could argue 2 or 3, but that's only 2, so really we shouldn't give anything beyond 2. However, I will accept 3 here, but you know, I'm not going to round that because that's beyond the maximum safe distance. So I'm going to actually round down here and say 104. Now, I know they're not asking you that, but that's what I would do. And if I'm on the ladder, I want it as safe as possible, okay? That's in feet. 100, and I would say 104 feet. I would not round that answer. The book probably, it doesn't even have it in there, okay, so we don't know what the book had. I would suggest going safe, because it's maximum safe distance. When you're dealing with safety, that is the place that you don't round up, okay? Good deal, thank you.
Thank you.
You finished, right?
Yes, sir.
Okay. Now, not that I'm going to, on a test, I'm not going to be picky like that, but just in real life, safety always fudged to conservatively. Okay. Were you going to say something? I'm sorry. Did you?
I was thinking, how would that save a life if you round down?
What's that?
How does that save a life if you round down?
Well, it could save both of your lives. That might be, if you're past the place that's safe, then you might lose control, and both of you go down to, if not a life, to a pretty bad injury, you know. So I think that's why they have the safety there. All right, good deal. That was the one that's not in the book. Let's do the one that is in the book. Any questions on that? It's not there for us to check, but pretty sure that's right. It makes sense anyway. Can't be any taller than the ladder, so that makes sense. All right, so let's actually do the one that is in the book, example 2. Now let me make sure this isn't their example 3. Oh, wait. This one is here, so we'll see. And they did it on top of the truck, but then they'll say that. And they'll say, yep, they use the sine function. And they said 110 times the sine of 72, which is 104.6 is what they said. So the maximum safe rescue height is about 104.6 feet above the height of the fire truck. And they threw that in because of their picture. I knew I'd seen their picture. Shows that some elevation too, so you get a little more distance out of it. Okay, but you see, same answer we got. All right, no, they do not have example 2, but we'll do the example 2 here. This gives us even more room to write. Okay. Finding the side of a right triangle. That's what we've been doing. Oh, by the way, every one of these examples has a checkpoint. Please do those after class, whenever you can, as soon as you can. The height of a mountain is 5,000 feet. Okay? I'm going to mirror their picture in case some of you don't have books. Do all of you have books? No, not all of you. Okay. So here they have the ground level, and then they have some mountain here, and they say this mountain is 5,000 feet high. Okay. The distance between its peak and that of an adjacent mountain is 25,000 feet. Okay? Now, you almost have to have the picture to tell. If I was reading that, I would think they meant the horizontal distance. That's not what they mean. They mean the vertical distance, the slant height. And they say that is the 25,000 feet. Mine's obviously not drawn to scale. I never would have, if I had been reading the problem with no picture, I would have done it elsewise. Okay?
Yeah, it doesn't say the other mountain is taller.
Yeah. The angle of elevation between the two peaks is 27 degrees. So the angle of elevation always goes above the horizontal, so this is our 27 degrees.
Maybe that's why they didn't use the example.
Right, I don't know. Okay, see the figure. The second question, what is the height of the adjacent mountain? So this is what we're looking for. How high, how tall is that mountain? Okay? Now they don't even label that in the picture. They should have. But that's what the question is. What is the height of this mountain? So, what would you do to get that?
Sine of 27 degrees.
Say again?
Sine of 27 degrees.
Okay, the sine of 27 degrees will give you this height, not the height of the mountain though, so keep that in mind. Okay? And how will it give you that? Sine of 27 degrees, I heard that said, so I'll write that down, is equal to what?
A over 25.
Okay, we're going to call that A there. A over 25,000. Okay, because that's the hypotenuse, and this will be in feet. So to solve for A, we'll multiply both sides by 25,000 feet. Okay, those will cancel out, and A is equal to what?
11,349.6.
So that 11,000.
11,349.
349 feet. That's our A there. But how tall is the mountain?
If you want to round up, it's 350.
350?
Yeah, 350.
Okay, we'll do 350. Ugly, but done.
Sorry about that.
Okay. See if I can clean it up just a little bit. Okay. But that doesn't answer our question. How high is the second mountain?
It should add that plus 5,000.
5,000, you got it. And that gives us 16,350 feet. And that's what they got to. Now, frankly, I don't think you have enough precision in the situation here. You only have 2 sniggers digits here, 2 sniggers digits there. You should really round this to 11,000, approximately 11,000 feet. Say that's approximately 16,000 feet. But this isn't a physics class. This is a math class. They don't pay attention to significant digits. But real life, you probably would. Okay? And they do have a checkpoint. Please do that. In fact, their checkpoint is very similar to the problem we did. Not exact, not the same numbers, but anyway. All right. from glancing ahead, they didn't do example 3 either. Any questions on 2 from the book? Okay.
I have a question about
Yes.
calculator. So
Not that.
Does this mean go that way 3?
Yeah, K means, yeah, okay. I see what, the other M meant milli,
Yeah, so go to the left.
and this is kilo, yeah,
Go to the right.
yeah.
Can your calculator do significant digits for you?
What's that?
Can your calculator do significant digits?
Probably not. No, I've never known a calculator that did that. You can set it for how many digits you want, and it'll do that, but it doesn't figure it out on its own. These are not smart calculators. Okay. Now, ready for example 3? Anybody? All right. Example 3. At a point 200 feet from the base of a building, so I'll draw the building over here. There's the building. And you're 200 feet from the base. Okay? All right. Corinthia? Yes. Okay. All right. All right. You're 200 feet. We're on page 329. This is still chapter 4, but the last section, chapter 4, trigonometry, 4.8 applications and models. And we're on example 3, which is the 4th example we've done, because there was one on the slide set that wasn't in the book, so we did them both. Okay, so here you are at a point 200 feet from the base of a building, the angle of elevation to the bottom of a smokestack, so there's a smokestack strangely here at the top of the building, okay? Right on the edge at that. So the angle of elevation from your position to the bottom of the smokestack is 35 degrees. All right. Whereas the angle of elevation to the top of the smokestack is 53 degrees, as shown in the figure. Find the height S of the smokestack alone. So this is the height of the smokestack. S for smokestack, I'm sure. Okay. Pretty heavily industrialized area, it looks like, too. Okay. How in the world are you going to do this?
What are they asking?
They're asking how tall is the smokestack. Any suggestions? It is not a one-step problem. I'll put it that way. Well, how would you proceed?
Find the angles. Find all the angles.
Find what?
That would all do. I would just find all the angles.
Find what?
Find the other angle first.
What? Oh, the angle between those two? You sure could do that, but what's that going to do for you? It might do something later when we talk about law of cosines, maybe law of sines, probably law of cosines, but it's not going to do anything for you now. So, any other ideas? Good thought, though. Say again? Height of A, which be the building? Is that what? Let's call it B for building, okay? So let's do the height of the building. And how could you get that? Given what we know.
Tangent.
Second?
Tangent.
Tangent. Okay, okay. My hearing's not good. So you're saying the tangent of
53 degrees.
eh,
Okay. 35.
35 degrees is equal to B over 200, opposite over adjacent. Perfect. Now all we have to do, multiply both sides by 200 feet. And that gives us B is equal to, anyone got it yet? 140, is that what I heard? 140 feet. Is that right? Now, does that make sense? Partly it does, because if that was 45 degrees, then these two angles, the lengths would be the same, and this is less than 45, so sure enough, it has to be less than 200. So I'm okay with that. All right? Now what? All right, if you do the same thing, the tangent of 53 degrees, that's now going to be B plus S, which is not the same as BS, by the way. Okay, never mind. Okay, B plus S divided by help me? Tangent by the 200. All right, your adjacent side. There's your opposite over adjacent. Again, that's going to be feet. So this is going to be multiply both sides by 200 feet. These go out. And B plus S is going to be what then?
Well, we know B is 140.
Right, we know B is 140. But this gives us B plus S. What is B plus S? Have you done it?
I got 265.4.
265.4. Let's just round that to 265 feet. Okay? Then subtract the 140, or is that right, 140 from that, and that gives you 125 feet. That seem reasonable? Now, wait a minute, though. Tangent of 53, can that be greater than 200? It's got to be, because 53 is beyond 45, so this side is longer than that side. Hypotenuse, it can't be longer than, but it can be longer than adjacent, for sure. 265 makes sense anyway, and we subtract that to get 145, 125, and they kept the 0.4 for some reason. I don't think you have justification for that, because in reality, we really don't have more than 2 single digits here anyway, so that 265 should have been rounded to 270, and then there's been about 130 feet. But we're not going to get that picky. Well, I sure can't see throwing extra digits out there. But again, on a test, you're not going to get it. I'm not that picky, you know, but I do. All right. There's a checkpoint after that problem. Then it moves on to example 4. Can I erase this one? Everybody see our procedure on that one? Okay. So let's do example 4. Finding an angle of depression. A swimming pool is 2 meters long, I can't read, 20 meters long and 12 meters wide. Okay? So I can't draw dimensionally very well. Let's just say get the long part this way. That's 20 meters long. Okay? And 12 meters wide, so I'm just going to represent it like this. Not a very good picture. 12 meters wide. Okay? The bottom of the pool is slanted, so the water depth is 1.3 meters at the shallow end. Now this is not drawn to scale. Okay? 1.3 meters here, which is fairly deep. It's not above your head or anything, unless you're a small kid. Okay, but at the other end, it's 4 meters deep at the deep end. So we'll guess that to be 4 meters. So I'll try to get that 4 meters here. So it's doing like this. So it's doing like this. And then there's some hidden sides back there. Okay, but this is the 20 meters this way, 1.3. 4 meters is the total depth here. 12 meters is the width. Okay? Now, find the angle of depression in degrees of the bottom of the pool. So that's basically saying if you had a horizontal line here, an imaginary horizontal line, what would be this angle here? You want to give it a name? Second? I can't hear. Want to give it a name? Nothing special, just make up a name.
Depression.
Second?
Depression.
Depression. How about angled capital D? Is that okay? I don't like writing a lot of letters. Okay. So that'll be our angle of depression. Okay. Now, how in the world are we going to accomplish that? Find that angle of depression. Well, it gets me depressed thinking about it, doesn't it? See any kind of relationships there we can use. Anything? Say again? Oh, okay. Help me, folks. I'm up here drowning. Huh? Never mind. Okay. I'm in the deep end. Okay. That is above my head. Anybody? See any triangle you might be able to use? That'd be helpful. Problem in trig class.
So do you see what would he use?
A triangle, maybe. The bottom one. Now, what do you mean by that?
It's cut off underneath.
Okay. But it only goes to here? Is that the one you mean? Okay. So what have we got to do?
We got to subtract 4 from 1.3.
Or the other way, 1.3 from 4, and that would give you 2.7 meters. Okay, I think we're making progress here. So we can use that distance. What other? We need 3 pieces of information. Huh?
20 meters.
Oh, we could use the 20 meters long at the top. Okay. New member to the class. You finished? Okay. You finished? Okay. All right. Oh, I really should put that here. I wound up not finding it later. Okay. So, anyone come up with a trig relation then we can use?
We use tangent.
Tangent, okay, because we've got the tangent of the angle D, capital D, is equal to what? 2.7 meters is the opposite side. Over 20 meters, that's the adjacent side. Notice your units go out, which is a very good thing, because tangents don't produce dimension quantities. None of the trig functions do, okay? So, how are we going to get what angle D is?
Well, if we subtract those, we get 0.135, or not subtract, divide.
Yeah, divide.
We get 0.135.
0.125 or 3.35, okay?
Then
Now,
we got to do inverse tangent.
inverse tangent. I wouldn't, whatever your screen gives you when you divide, and it probably will be exact. Yeah, it will be exact. And then do an inverse tangent of this, or arc tangent if you like the way the book does it. That should give you the angle D. What do you get? What's that?
It's 7.69.
7.69. I hope you're in degree mode, right?
That's degree.
7.69 degrees. Now, I would argue we don't have more than 2 significant digits anywhere, so I would make this approximately 7.7 degrees. All right. Oh, you can't just get it? Okay. Okay. Did you have this piece of paper? Is that yours?
I think so. I didn't remember.
Okay. All right. Now, you can go, that office right behind here would be okay, or the office behind it. That class over there is pretty loud, so you might want to go there. Turn on whatever light you need. Okay. And how did the book do? They put 7.69 degrees. Shame on them. They don't pay attention to significant digits. Okay, there is a checkpoint there. Please do the checkpoint. Okay. Now let's move on to trigonometry and bearings. Okay. In surveying and in navigation, directions can be given in terms of bearings. Okay. A bearing measures the acute angle that a path or a line of sight makes with a fixed north-south line. So I'm going to stand approximately north-south. This is close. May not be real close. Let's just say that's where we are. Okay, this is north-south. Now what if I want the bearing to the projector there, the bulb or the lens of the projector? I'll go from north, this many, maybe 15, 20 degrees, something like that. That'd be, and I'm going east of north. So that'd be north, because that's the direction I'm facing, 15 degrees east of the wind that direction. Okay. Let's say I want the door back there. That would be face north, goes this way. That looks like maybe about 35 degrees north, 35 degrees west, of the west. But what if I want that edge, or this edge of the chalkboard, the graph board here? Well, I don't want to use north, because that's not going to give me an acute angle. So I'll turn around and do south, 20 degrees east, because now I move to the east. Or if I wanted to do the corner of the window right there, I would go that way. So that would be south, because that's the direction I'm facing, and maybe 25 degrees west, to the west. So that's how we measure these. Bearing measures the acute angle. It has to be an acute angle. That's why I didn't do obtuse. It would throw my shoulder out. With a fixed north-south line. So you can either be facing north or facing south, and then the angle going so many degrees either to the east or to the west. So always the first letter is a north or a south, which way you're facing, and then the number of degrees, whether it's to the east or to the west. Okay, so this would be a south, 35 degrees to the east, a north, 80 degrees west, a north, 45 degrees east. All of this makes sense. Now, if we're 90 degrees, you could just say due west. You don't have to use the north then, or north 90 degrees west. That would be due west. Because you could face either south or north and you'd still be 90 degrees to the west. So I would just shorten that. Due west. Okay. All right. Example 5 here, and that is the same one in the book. I need to check now. A ship leaves port at noon and heads due west, okay, at 200 knots. Now, anyone know what a knot is? They give it right there. Nautical miles per hour. What in the world is a nautical mile? Does anyone know that? And I don't know why this is the case, but it sure makes a lot more sense than statute miles do. A statute mile is how many yards? Does anyone know? Or how many feet? A regular mile here on land. Anyone know that? Second?
5,280.
Yeah, feet, exactly. That is a statute mile. A nautical mile is 6,000. They rounded up, went up to the next thousand. In yards, a mile is 1,760 yards, 2,000 yards. Okay? Just makes a lot more sense, okay? And that's what it is. So that's what a nautical mile is 6,000 feet or 2,000 yards, and a knot is a nautical mile per hour. So 20 nautical miles 20 knots would be a little more than 20 miles per hour, maybe 25. Doesn't really matter, but that's get an idea. So, ship leaves port at noon, heads due west at 20 knots, nautical miles per hour. At 2 p.m., it changes direction. So how far did it travel in those 2 hours, from noon to 2 p.m.? Not that hard. 20 nautical miles per hour travel for 2 hours. Pretty easy.
It's 12,000.
So again?
12,000. Use 6,000 times 2.
Yeah. 20 nautical miles times 2 would be 40 nautical miles. You don't need to go to feet now. Just use nautical miles. I was just asking you what a nautical mile was. Okay. You don't need it in this problem. 40 nautical miles due west. But at 2 p.m., 2 hours later, ship changes course to north 54 degrees west. So this is the new course. Face north, 54 degrees west. Okay? So this is where it's taking off now. Okay? It's shown below. Find the ship's bearing and distance from the port of departure, that's A back there, at 3 p.m. So they only travel 1 hour here. So how far do they travel? In nautical miles? 20 nautical miles. So there's our situation here. Now they're asking two things. The ship's bearing. Oh, I thought there was a question. Ship's bearing and the distance. Frankly, I think the distance is easier to do. Okay, but it doesn't matter. We'll do them both. Okay. So what we got to do now is find out how long C is. Now, this C is not a hypotenuse. Don't think that's that. It's just because that is the, well, it is. It's the hypotenuse of this capital C. Okay? It's not the hypotenuse of this. It's the hypotenuse of that. Okay? So again?
That's not a right angle.
No, that's not a right angle C, but it is. This is a right angle. Okay, so it is the hypotenuse there. Okay. Now, so that's one thing we want to know is C. The other thing we want to know is the angle between due north and this. So they don't even put it on there. That's going to answer the first part. What is the ship's bearing from the point of departure? So this angle right here is going to be the first thing they're asking for, but it's not necessarily what we're going to do. So this angle, and I want to call it theta, so let me call it theta. You can call it anything you want to. Okay? Now, how are we going to get either one of those? Any ideas? Already the hint is given here when they use C and put a letter C here that's not anything to do with the ship never went to sea. Okay?
Yeah.
Well, it did. It went to SEAC. Okay. But, so, how are you going to proceed? They've already almost given it to you. When you notice, they don't pay a bit of attention to anything back here. You start right here and deal with this triangle right here. In fact, they refer to this side as B, referring to this angle. Not quite right, but we'll let that go. No. It depends on what you call it. This point is B. A vertex is B. But dealing with this angle here is your angle B.
Okay, so that angle, you 180 minus 54.
Perfect. This angle right here that they're called B now is
26 degrees.
Wait. Say that again. What you
I
said?
think it's 26 degrees, right?
Not quite.
90 minus
36 degrees.
36.
It's 90 minus 54. 36 degrees. Right? So that's our angle B here is 36 degrees. Okay? And then the angle C, of course, is your right angle. And now we can do, okay, we got to do two things with that, right? What two pieces of information do we need to know? Okay. You know this 36 degrees, you know 20 nautical miles, and you know the angle C. What do you really need? And there's two pieces you need.
The lowercase d.
The what?
The lowercase d.
The lower, okay, we need that later. We're not even close to that. Not with this triangle, you can't get it. As soon as we get some information on this, we can get that. But not at this point. What do we need?
I guess
What will this give us? Huh?
the length of lowercase b.
Lowercase d is one thing, because then we can add that to this, and
That's what
that's
we just
one
said.
part of getting towards C.
Right.
Okay? And then another part would be lowercase b. Okay? Because then we'll have the opposite side, and these two added together adjacent side, and we'll have our C. So we need both of those. Which one you want to go for first?
Getting lowercase d is easy.
Lowercase b first?
Lowercase d is
D first, okay? Let's go for that. What would be a relationship, a trig relationship, that relates lowercase d to the angle you know, 36, and the hypotenuse, 20? Cosine. And how would that go then?
d over 20.
Cosine of
36.
36 degrees is equal to d over 20. Is that right? Yay or nay?
Yay.
Yay! All right, we got it right. And then what do we do? Multiply both sides by 20, and these are 20 nautical miles, by the way. Multiply this by 20 nautical miles. Okay? These will cancel out. Okay? What does that leave D to be?
16.
16? Is that what you said? 16 nautical miles. Okay? What do we need next? B. And how are we going to find? Need to find a relationship between the angle we know, 36 degrees, and the, and what?
And the side. So d
Sine
sine.
of 36 degrees. So let's do that. The sine of 36 degrees is equal to
B over 20.
b over the 20 nautical miles. So we'll multiply both sides by 20 nautical miles. Okay. And what will that give us? B is equal to?
12.
Second?
12.
12 nautical miles. Okay. Now, a little time out here. We did it this way. There was a way we could do it without having to count on our subtraction. Anyone know what that is? What? This angle right here is 54. Have y'all ever heard of alternate interior angles from geometry? These two are parallel lines here. That's a transect or whatever you call it. Cuts those two. The alternate interior angles are the same. So we could have done the same thing from this one. But since you told me subtract it, we subtracted it. But we could have used that 54 and gotten the same results. And that way you wouldn't count on not making a mistake with your subtraction. But I was pretty sure we hadn't made a mistake. So we're okay. Okay. This still hasn't told us the bearing, nor has it told us the distance. Is there any way we can get that out of it? Say again? How? Anybody?
So we need to find lowercase c.
Say again?
Lowercase c is the distance, right?
Is this distance here?
No, I'm talking about like the distance from the port.
Oh, I think we can.
This is for the force is lowercase c.
Yeah, that's
That's what we're looking for.
Yeah, so we need to.
I think we can add lowercase d and that 40.
That's it. Okay, add those two together, and that gives us 56. Okay, nautical miles. And this is 12. How do we use that?
The new bigger triangle.
The what? You're so close. Say again? I can't hear.
12 squared plus 56 squared.
Okay, Pythagorean theorem. 12 squared plus 56 squared. That's going to give you some number, and then you do what? Take a square root of that answer. And what do you get? C is equal to the square root of 12 squared, which I know is 144, plus 56 squared, which I don't know at all what that is, and then take a square root of that. And what do you get?
57.
Say again? 57? 57 nautical miles. Now that doesn't seem like a lot. You're only getting one more nautical mile from this. But see, that's a pretty small angle. But now that we know C, that's the distance, like I said, that's the easier one to get. Now let's get the bearing. So what are we going to do here? What we know now doesn't give you that angle theta. Okay? What we know now relates this length, that length. I wouldn't use that because that's a derived length. And both of these are sort of derived, but you derive that one from these two derivations. So
Yeah.
I would stick with this one. That will give you this bearing. That bearing there, I mean that angle there is not a bearing. That's the bearing. This angle here, you want to call it something else? How about theta complement? Would that be okay? Okay, theta complement. We can get that. How do we get that? Anyone see a trig relation that might give it to us? Anybody? Okay. Now, all three sides of the triangle. Surely we can come up with a trig relationship that deals with theta complement. Anybody? Please, somebody. I'm drowning in there. I'm out here in the ocean, okay? I'm not even in the boat. Somebody, give me something.
We're done.
Surely. There's an angle, and you know three sides. Surely you should be able to give me some trig relationship between that angle and two of those sides. Any two you want to. Tangent. I like tangent, okay? One of my favorites, okay? Tangent of this angle theta complement, I'm calling it, is equal to what? What is the tangent?
56 and 12.
Say again? What is the tangent?
Tangent is opposite over adjacent.
Opposite, taking oats away, remember? The opposite, which is 12 nautical miles, over the adjacent, which is 56 nautical miles. Okay? Nautical miles go out, which is good because tangents don't produce dimension quantities. And then you'll do an arc tangent of this, or inverse tangent of this, theta c equal to inverse tangent of, I'm going to reduce that because I don't like big numbers, 6 over 28, which would be 3 over 14, I think. I hope I did it right. I'd rather use big numbers than make a mistake, but I think, see, 4 going to that and 4 going to that one. Yeah, I think that's right.
Yeah, that's
Second?
3 over 14, that's right.
Okay, thank you. What will that give you? Arctangent of that? 12 degrees. But we don't want that angle, we want theta.
Yeah, that's what I'm confused.
So we
Subtract the 12 from 90, and you get, because they're complementary angles, that's why we named it theta C. Theta is equal to,
Point me to 90 degrees. Where y'all talking about?
okay. See, this angle plus that angle is your 90-degree angle, right? We did theta complement, so we want to get theta.
That doesn't even look like it was remotely for 90 degrees.
I'm going to get a different color here. Red, is that okay? Let's go. This, well, that didn't get red, did it? Okay. Okay. Do they look remotely somewhere there?
He's talking all the way to the right of
This is your theta, and this is your
Oh,
theta.
okay.
Okay? That adds 90. Subtract 12 from 90, and you get 78. So we got this is 70. Let me go back to dark. 78 degrees. So then what would be the bearing? You got to get the bearing the way we say bearings. Which way are you facing first? North. 78 degrees. In which direction? West, exactly. North, 78 degrees west. Let's see what, oh, we can see what the book got. All right. Now, they may have done it slightly differently. I was following your leads here. Maybe got me in serious trouble here, but let's see what happened. From the triangle BCD, see, we went right to that triangle. From that triangle, you have 90, they did it the same way we did. 90 minus 54 is 36. They did it the same way. I was guessing they were going to use the 54 from here, but they didn't. Perfectly fine, okay? And then the two sides of the triangle could be determined by B is equal to 20 times the sine of 36 degrees, which we did. Back here, somewhere, there it is. B was 20 times the sine of 36, and that D was 20 times the cosine of 36. And we got, goodness gracious. Good deal. Thank you. You finished?
Yes, sir.
Okay. And then they didn't come up with numbers. They just kept the expression in there. The V was 20, 36, and divided by this. Really a weird way to do it. But anyway, they came out. Let's see what they got. That was their tangent. They took the inverse tangent of that arctangent and got, oh, they got it in radians. How wonderful, since everything was in degrees. 11. We said 12. Okay. Okay, 12 degrees. And then the angle was 78 degrees, and we said that too. So the bearing is north, 78 west. Oh, fantastic. Thank you so much. All right. And then finally the triangle, and we got that. Oh, they did it with trig rather than Pythagorean theorem. Let's see what they got. 57.4, which we got 57 nautical miles. Very good. All right. So we'll start next time with harmonic motion. Homework exercises here will be any of the odds, 5 through 11. They're all at Calc Chat. 9's at Calc View. Any of the odds, either 13 or 15, they're both at Calc Chat. 15's at Calc View. Any of the odds, 17 through, goodness gracious. Let's see, maybe about 31, 39, any of those. Do some of them that have to do with distances and angles of elevation, and do others that have to do with bearings and stuff. And we'll pick up the rest of those next time. Now, I have a question for you. Do any of you want to test to work on during the weekend? Okay. Let me run down to the copy room. I left it in there to be copied, but it wasn't copied when I was last down there. Okay, so we'll just put it right there. We'll be fine. And let me run get that, and I'll be right back.
You talking about the grading?
One that you're talking about.
Oh. Yeah.
Great, that's right. First test was on Blackboard.
He's already on Blackboard.
Yeah.
First test.
Mine is this.
You start getting on Blackboard.
A lot of numbers.
Stuff like this.
What? I'm doing good. I'm good at geometry after now. Looking at those pictures, so start hurting my head. Doesn't matter. What malfunctions if it goes off the table?
It's just gonna be silent.
Okay, sorry. How many wanted the test now? Okay, now this has a fair amount of graphing on it. So I've got some graph paper here. If you need it, if you have your own graph paper, you can certainly use that too. I'm so sorry those people who left early didn't get this opportunity, but it's all right. Okay. They may have had another class and they didn't want to be late. Okay. Y'all need some graph paper. I know it's in here somewhere. Okay. Anyone need graph paper? Okay. Okay, it's front and back. Now there's 9 to graph. So if you get a piece of front paper, do 4 on one side, 5 on the other. You don't have to make super big graphs. Anyone have any graph paper? Okay, you do. Okay. All right. And if you need more, come see me. I'll give you more. I just ran out. Okay. I mean, I didn't run out. I just only had to make so much. Okay. Let me turn off the projector here. Turn off the